This is part 2 of our discussion of electrostatics. A neutral body is a body in which one has equal amounts of positive and negative charge. Be careful. Students often think that when something says that it has no charge, that means there's no charges. That's really bad. It's no net charge. There are always charges in every object. One of the most fundamental things we know is that matter is composed of atoms, and inside atoms there are positive and negative charges. Huge number of charges. 12 grams of carbon is 1 mole, and 1 mole has 6 times 10 to the 23rd atoms. Now, in that 6 times 10 to the 23rd atoms, there are basically 6 protons, which are positively charged. So we've got something on the order of 3.6 times 10 to the 24 protons, positive charges, in that 12 grams. We have an equal number of negative charges. So there are a tremendously large number of charges in any object that you have. It just so happens that in most cases the amount of positive charges and the amount of negative charges is amazingly balanced. I mean, balanced to parts per 10 to the 20th or such. But it's possible that maybe one part in a quadrillion or so is different, slight imbalance, and yet that creates a tremendous force. You never take off half the charges or a third the charges. Just a small difference will create a huge force. So here we've got 4, but that really represents like 4 times 10 to the 25th charges. Same number of red ones, same number of blue ones, so the net effect is it's no net charge. Now, we'll come back to this because it's important to understand this in dealing with charging by induction, that there are these charges, and if these charges not only differ in number, but if they're not exactly staying on top of each other, if they're even slightly separated spatially, it can create the ability to have forces. Like charges, we find out, always repel, and unlike charges, attract. So if you have an object that has some positive charges, and there's another object that has a net positive charge, these two objects will repel each other. And this force that body applies on the second is equal and opposite, that is equal in magnitude to the force the second body applies to the first. They're both electric forces. They have to be the same type, and they point in opposite directions. This is just the third law of Isaac Newton. On the other hand, if one of these is a positive charged object and the other is a negatively charged object, then in this case they apply equal magnitude forces in opposite directions, but those forces are attractive forces. This positive charge is pulled toward the negative charge, and the negative charge is pulled toward the positive charge. Notice the third law is alive and well in electromagnetism, that is in statics. Now, Coulombs Law. Point charges tend to show up a lot. So we have this problem where there's this one charge over here, call it Q1, and there's another charge over here, call it Q2. They could be plus or they could be minus. And there's a distance between these two charges, and that distance is R. The magnitude of that force, F, can be found as 1 over 4 pi epsilon naught times the magnitude of the first force, the magnitude of the second force, divided by R squared. Now, a lot of people will put vector signs, eliminate these absolute values, and then put an R hat. That's totally true and correct, but I don't find that it works as well for students at this level. So here's the thing. Don't put any plus and minus signs in here. We'll come up here and decide which way the force pulls, and we'll put the arrow in our free body diagram, just as we did other forces. But we just need the magnitude, like we do with mg for weight. So what we need is the magnitude of the charge here times the magnitude charge of the other, divided by R squared, and this 1 over 4 pi epsilon naught. The 4 pi really belongs to the R squared. It's the surface area of a sphere, and it tells us that this equation is special. It only works for point and spherical charges. The epsilon naught is a proportionality constant that describes the strength of the electric force. And it is called the permittivity of free space and is provided on exams. Now, because this thing has a really difficult value, this permittivity of free space, although physicists like to write it this way, in books at this level we'll generally combine the 1, the 4 pi, and the epsilon naught and make it just one constant. When we do that, the equation has an even simpler form, and that form is F equal K Q1 Q2 over R squared, where K has a really nice number, 9 times 10 to the 9th Newton meters squared per Coulomb squared. 9 times 10 to the 9th is easy to remember. The permittivity of free space constant was not. All right, so K Q1 Q2 over R squared. If you have to chant it, memorize this formula. It is an extremely useful and powerful formula. Memorize. We'll come back and talk about the form of this equation and why physicists find it so important in a later video. Coulombs law is limited to point charges or spherical charges. It's not a universal thing. However, it forms the basis of many other techniques. In fact, if you were patient enough or fast enough like a computer, more complicated problems involving rods or plates or lenses inside a television set could be solved using this technique. What one would do is to break up a more complicated problem into a sum of point charges. So let me show you that. Let's say that you had something that looked like some sort of a bar, and you were interested in finding the force on some charge up here, Q. What we could do is we could break this bar into a string of small point charges. So there's one, and that point charge has some distance r. Here it's r. I'll call it r1, and it's going to apply, say, some force F1. You could treat this charge right here as a point charge, and it likewise has some r. Maybe that's R10, and it likewise has some force, F10. And so by adding up the little vectors from each force for each one of these little boxes, I could approximate the solution for a bar that I don't know the answer to. Now this may seem really difficult and boring and hard to do by hand, and it would be, but for a modern computer that can do a quadrillion calculations a second, it's just child's play. So no problem at all. And so many techniques actually use this ability. Alright, that's it for Coulombs law. In the next video we'll actually do some examples.